sorry, this 1 second. Right. So this morning, Spear has given a very nice introduction on the cuprate pseudogap. And what we are interested in is, so the pseudogap has shown many properties, like it emerged in the region below the critical doping level P star and critical onset temperature T star. And there's an energy gap, depletes the density of states. Also, the magnetic stability, electronic specific heat, and the C-axis conductivity are suppressed. But all these properties have not been well explained by one single state. Until recently, there is a PDW state that emerged that possibly can suit this picture. That's the motivation for our project. And in the past 10 years, there have been increasing proposals that suggest the cuprate pseudogap is a pair density wave. It's first proposed by Patrick Lee of the unpaired pairing paper, and then followed up by the quantum oscillation model, and then a phase fluctuating PDW still by Patrick Lee. Also, then Peter Hirschfeld followed up using a RMFT model in 2020. And last year, Sebastian, she found there is a current at high magnetic field. This could also be a possible signature of pair density wave. And then there are two, right? Yeah.
These authors use the word pair density in a very different sense, right? Like Patrick Lee is talking about a pair density wave in which the uniform component of the intensity of the superconducting autogram is zero. It's entirely oscillating, whereas Shuqiu et al., I think, means something that has a background and then an oscillation on top of it. Right. So which sense are you using in both senses, or
so the one Shuqiu used, he firstly made a model of PDW coexisting with DSC. That's his model in 2017 and 2020. And then the one I work with him that I will be discussing in the next 10 minutes is the one of a pure PDW, where the DSC is gone. I'm looking into the region about TC. So there is no uniform DSC. That's a new paper. Yeah. So that's two more theories on this topic. So a Cooper pair density wave state is a superconducting state which the order parameter varies periodically as a function of position. The order parameter it has non-zero momentum Q because they arise from the pairing of quasiparticle at momentum K and minus K plus Q to form a Cooper pair with central mass momentum Q. It's very similar to an FFLO state that is formed when the Zeeman splitting of the Fermi surfaces leads to the formation of Cooper pairs. So the gap function of PDW modulates sinusoidally, and it induces a CDW that also modulates sinusoidally, but it has a different periodicity. That's about 4 unit cell, whereas the PDW is 8 unit cell. Also, it intertwines with the SDW that modulates at 8 unit cell, and it changes signs. It has phase shift with respect to the PDW. So PDW is a phase of matter that is defined in terms of broken symmetries. The PDW is distinguished as from a CDW that coexisting with DSC because the spatial average of PDW vanishes. And this is the first experimental motivation to search for a PDW in LBCO. It is the neutron scattering experiments carried out by John Tranqueda that there is resistivity anomaly at the doping level of 1/8. So this is more characterized by an anisotropy between the in-plane resistivity and out of the plane resistivity. So this behavior can be explained by the stripe order associated with PDW. And this is the model proposed by Berg in 2007. So it's a stripe order, and inside of one LBCL unit cell has two planes. So one plane has stripe like this, and the second plane has stripe rotated by 90 degrees. And in the second nearest plane with respect to the first, there is a phase shift between the superconducting order. And that's the anti-phase superconducting order in such stripe order occurs the decoupling of the Jones-Upson junction between the planes. And that's how this model can explain the 2D superconductivity. So a few experiments from my group have shown an STM evidence of an 8-unit cell PDW state in the superconducting region in BISCO. 3 experiments are carried out in this region at a doping level of 17% at a temperature either at 4K or 50 millikelvin. And the first experiment is using SJTM to look into the electron pair density, which modulates at 4-unit cell. The second experiment is that they search for the presence of an 8-unit cell PDW inside the vortex hollow. So that's the location where the superconductivity is suppressed. But it shows a strong 8-unit cell PDW. And the third experiment is using a superconducting tip to scan BISCO that shows gap modulation at 8-unit cell. But none of these experiments are carried out about TC. So that's the goal of this project, is to visualize the temperature evolution from the low temperature region about TC to the pseudogap region. And we'll be searching for the PDW signature of the quasiparticle interference pattern and the gap modulation in the non-superconducting pseudogap phase. This is the method we use called quasiparticle interference. So firstly, I can play this movie. Using STM, we take a differential conductance spectrum at a field of view about 40 nanometers from -34 millivolts to 34 millivolts. And then there is strong setup effects in STM when measuring the cuprates. So we calculate the Z map, that is the ratio between the two conductance map at the at V and -V. And then by taking the Fourier transform of the Z map, we can see the QPI pattern for this. So this is the Borg-Liouville scattering interference that occurs when an impurity atom scatters quasiparticles. It interferes to produce the modulations surrounding each scattering site. So each local maximum in this movie, it reveals the set of energy dispersive wave vectors generated by the scattering interference. An efficient way to sum up all the scattering interference wave vectors is the lambda map that we summed up to delta naught, that is the energy where the Borg-Liouville quasiparticle no longer exists. This will be focusing on this one. It provides a fingerprint of whatever ordered state that controls the wave vector.
Delta naught is measured how? Zero temperature?
Delta naught is measured at 4K. So it's about 28 millivolt. And this is the model by Chobe. So that's his original model of coexisting PDW and DSC. It is based on a renormalized mean field theory of the TJ model. So the T is the hopping rate and J is the Heisenberg exchange. Here, PG, the operator, eliminates all doubly occupied orbitals. And here, the PG is replaced by the spin and charge renormalization factors variable by atomic site. And this Hamiltonia is decoupled into a diagonalizable mean field approximation using the on-site whole density bond fields and electron pair potential. And this model is initialized by PDW at 8 unit cell as we measured from experiments. The outcome of this model is the prediction of the net charge, such as this one, and the bond order field and electron pair field, this one. And also they use Vernier function to predict the quasiparticle density of states at each atomic site. So that's the first paper in 2020 where the STM experiments can be reproduced in this RMFT model. And so last year, what we did is to add a temperature to look into the electronic structure here as a function of temperature. So what we found is that at about 0.05 T, the order parameter, the uniform Q factor of the DSC significantly decrease, whereas there is still a strong PDW here. And then at about 0.085 T, the DSC apparently vanishes to 0, and there is still a PDW. So the key message here is that there is a pure PDW about TC from this model.
Which I and delta. So in the PDW phase, which is not there.
Delta is the electron pair field.
It is also there. It's only at some wavelength.
So there are two of them. The Q equal to 0 is the DSC, the uniform one, and Q equal to QP is the PDW.
And so that's the PDW phase, the highest temperature one. Only that is non-zero.
Yeah. And then that's our experiments. We measured from 4K up to 55 Kelvin for a viscous sample that is 8% whole doped. That's basically a temperature evolution from the superconducting phase to the pseudogap phase. It's measured from this field of view, and then we measure the differential conductance to calculate the lambda map, which is the QPI. And here, delta 0 is the critical energy we summed up to. So it is about 28 at 4K and about 20 millielectron volts at 55 Kelvin. And that is the delta 1, that's the pseudogap energy scale.
Why are you summing up? Just to reduce the noise or what?
It's just to summarize all those and the dispersive energy wave vectors efficiently.
You have a lot of more data. Why do you want to reduce the data?
So I think this is following the technique that they developed in 2014, which you also discussed this morning. Below the TC, by using the sum up technique, they can use the Q4 wave vector to trace the Fermi arc. That's just an efficient way to sum up all the 7 octlet wave vectors. But of course, we can try to decompose the wave vectors. It's a bit complex, so we haven't figured out how yet. And next is that we measured the gap modulation of delta 1 of an 8 unit cell PDW plus DSC at 4K. So delta 1 is defined as this energy scale at about 80 millivolts. And then this is the scale of the gap map. And the white region are the region where the gap cannot be defined. By taking a Fourier transform of the gap map, there is 8 unit cell modulation along X and Y direction. And Fourier filtering of the 8 unit cell peak also shows modulation in real space. Next, we looked into the electronic structure. So basically the differential conductance map. At about 5 Kelvin in the superconducting phase, the electronic structure between the superconducting phase and the pseudogap phase, this is 55 Kelvin, are almost the same. So we think the PDW that exists below the TC continues to exist above TC. And this is the gap map. The spatial distribution of the gap appear to be quite similar, except in some region at the high temperature, a lot of the gap cannot be identified in some of the regions. Second, we start to carry out the experiments to measure the QPI pattern. This is measured at 4K. We measured 6 movies at the same field of view from 4K to 55 Kelvin across the TC. From these 6 movies, the lambda map QPI is calculated. So it's the temperature evolution of the lambda Q from superconducting phase to the pseudogap phase. So the interesting thing here is that across the TC, nothing dramatic happened. So this implication is that the ordered state that exists below TC continues to exist above TC. And similarly, the model of PDW plus DSC predict the QPI pattern for this, predict the QPI pattern for PDW state independent from the experiments. That's the QPI pattern. They appear to be in good agreement. Also, at TC, nothing dramatic happened.
So this theory model, delta Q equals 0 vanishes at the red line.
Yeah.
And then above, there's only delta finite.
Yeah.
Okay, and what is the difference between the two? Is there any clear-cut difference between below TC and above TC, or there's no very little difference?
So I'll show this in the next slide. So quantitatively, the difference between below TC and above TC is the length of the arc feature. So that is the one here. Yeah, there is a significant increase of the arc length, both in experiments and theory. And we measured the arc length by calculating the angle of this arc. The angle of this arc that subtending from here to there. And then this is the temperature evolution of the arc length. So there's clearly there's an increase of the arc length. Now, what is the actual physical meaning of the arc? We are not sure yet, but this is showing an increase of the length of the arc. And then we looked into the QPI pattern about TC. So in the middle, there are 2 QPI patterns measured in experiments about TC. And this one is the prediction for a pure PDW. That's also when the uniform factor is gone. And this one is the prediction for a pure CDW. that the CDW cannot be generated from this model self-consistently, so it is input by hand. And by looking at by eye, the experiments of the pseudogap are in much better agreement with the PDW QPI because of the arc length here. That they both have shorter arc, whereas the CDW has arc reaching 0. And also
this is a CDW on the full large Fermi surface state. So what I was suggesting this morning, perhaps you should, no one's done that calculation, but you should do it. You put the CDW on top of a full pocket state, some FL star state. Okay.
Oh yeah, we might
But how
consider
about
that.
4 intense things in the center? I should ignore those.
Oh, that's a very good point. That's the charge order. So I can show you here. So in experiments, this is the charge order peaks separated in the predicted QPI map. When the calculation take into the charge order peaks, it is so strong that it's that when it exists, we cannot see the PDW order. Can you see some of the dots here along the nodal point? Maybe the contrast is not strong enough, but basically when the charge order is present, it will be too strong to see the PDW order. But when the charge order is suppressed, we can see such nice pattern to be compared with the experiments. That's why these 4 spots are suppressed in this theory. And moreover, because it's a short range ordered CDW, so by taking into that effect, the 1/4 peak might be gone in a normal model. This is a qualitative comparison between the experiments and the theory. So by putting the theory onto the experiments, the spatial distribution of the quasiparticle features are in good agreement. Particularly, the arc lengths are in good agreement, and the presence of the nodal quasiparticle is also in good agreement. And usually about TC, there's nodal quasiparticle here. It has both disappeared in the theory and experiments. That implies the nodal, but that implies the uniform DSC factor. So in conclusion, the scattering interference pattern indicates the pseudogap contains a PDW state. The conclusion is mainly drawn by comparison of the quasiparticle interference pattern between the experiments and the theory, and the pure PDW provides a much better support for the experiments. That's it.
Question?
No, that was, what about, suppose I took the PDW and did the correlation spectrum, can you explain the correlation? Before the arcs, I showed you correlation this morning. Can you get that from the PDW?
So I think it from the theoretical point of view, I think in Patrick Lee's paper, he suggested some possible PDW.
Yeah, he was explaining the anti-nodal region.
Yeah, right. Yeah.
But not in the nodal region, the PDW theory just doesn't work.
I see.
So maybe that's not a bad question, because, but that was a different PDW, maybe this PDW, this is period 8, right? I don't know if that could be something else.
But experimentally, this is what we are thinking. So about TC, there is a phase fluctuating PDW. That's the PDW order parameter, where the phase will be a random number about TC that in maybe 10, 20 Kelvin about TC. This will cause us the formation of small patches of PDW here and there. And between each patches, there might be no correlation. That will be the difficulty to find it in experiments. But suppose we can find such PDW, this short patch of PDW in experiments, we can look into it in Harper's. I believe it might has Fermi arc and the gap taut area. But it's a future project.
Related question that may not be really related, I'm not sure. If the phase is not fluctuating, let's say you have phase coherence, do we see a nice makeup? It's a superconductor.
Yeah, I think there's a paper that suggests that there is Meissner effect of short-range PDW, but without supercurrent. There is a theory paper.
Without the supercurrent, we can analyze it. No. Meissner, we need the supercurrent to screen the level. But it's modulated in space. So is that normal?
No, but it has an overall phase data there. That can be twisted.
Right.
So it can carry the superconductor.
Right.
If it's got a stiffness.
But you have modulations in the real space as well. Amplitude is self-modulated. So is there a way that one can make phase to be coherent and then generate this it's like a velocity?
Presumably the coherence then has to be larger than the period of the density wave.
No.
Otherwise, the nodes would completely kill the supercurrent. But I think this will be the first established example of the fair density wave. Is that just to throw the question out that under what circumstances does a superconductor prefer to modulate its gas like this? What is it? What is the energy scale that's keeping confident? You think normally you should cost kinetic energy, right? But it's obviously gaining some advantage in some respect. Is there a simple way of understanding how the approach to multi-insulator favors a fair density wave?
So in this model, although the energy of PDW is slightly above, is more energetically favorable than DSC, but that's because it's not the ground state for in this model. The energy scale between DSC and PDW are very close. The DSC is still the ground state for this model. To exactly the energy balance, we will need to look into that in the future, but that wouldn't change the physics related to the QPI patterns predicted from this model, I think.
So what's the wave vector Q here?
It's from it's our experiment measure. It's wave vector at 1/8. So we just input 1/8 into the model.
1/8
1/8
and the y, or 1/8
1.
y over 8, right?
Yeah, right.
In both directions or one direction? A diagonal or A and B axis?
I think it's one direction.
One-
One direction. Like this is the right. That's the predicted 1/8 unidirectional PDW.
So there would have to be a phase transition into this state, even if it were a discrete order. Well, it's very breaking, it's fragile symmetry.
It's a short range.
I don't know. What do you mean short range? In the picture, I can't tell the difference between as and long range order. It looks difficult to tell. It looks like it has long range order. Well, there are two features here. One is the Q vector pointing in two discrete directions, and the other is the stiffness of the phase, right? Now, a priori, they don't have to develop at the same time. So clearly, when you talk about a pseudogap as being a fair density wave, you clearly don't mean that it has long range order of the phase. So it's obviously not a superconductor. But I think you're implying it has discrete orders. The Q vector is stuck in the X direction or the Y direction with well-defined domains, right?
Yeah.
Right. So if those domains are really big, then you ought to have phase transition into the state. Of course, disorder could mess things up something that locks the Q vectors together.
Maybe that's why it's called glass, like a PDW glass.
You know, CDW glass is a superconductor. That's a vice versa.
PDW glass.
A PDW.
Maybe the phase coherence is from a superconductor.
Glass.
That is different from the amplitude of it.
Well, if it's a glass, it means the phase theta is a function of position but not on time.
I see.
That's
So
a-
you have
that
some
is
phase
that
coherence.
is a superconductor.
Okay, I see. I mean, so what is this then?
This is I mean, what you're calling a PDW is also a superconductor. It should have a superconductor.
It's just small regions of
Yeah.
PDW. It doesn't have long range order.
Right.
Raises the question of whether the discrete order has set in without the phase order.
But that is the CDW. The discrete order is the CDW.
CDW.
The square of the PDW is the CDW. Oh,
Or the other way around? No,
I see.
I see.
Do you see any clear sample variation of the correlation then?
Above or below TC?
In the PDW. I mean, isn't it so if you heat up and cool down again, the images are pretty reproducible, right? And
Yeah.
what kind of textures are pinned by some heat up.
I think there is predictions of PDW versus doping level. But for the moment, we haven't been able to see it in experiments as yet. But that's what we plan to do at Oxford, is to search for PDW in the underdoped cuprate.
Okay. Thank you very much.
Thank you.
And that brings our program to a close today, at least the formal part. And we will return tomorrow at 10 in the morning.